Thank you all so much for your attention. I'm sorry that I'm not able to be there with you in person, but I look forward to the opportunity of getting your feedback on our approach to this work after we go through this presentation. This work is a proof of concept study that we're doing to determine the enablement effect of semiconductors in terms of greenhouse gas savings. I've worked with a graduate student, Ms. Weitong Liu, on this work. We are both within the Department of Material Science here at MIT. I believe you all know the motivation of this work. We were approached by ITRI and TSIA to do a proof of concept to understand the potential greenhouse gas savings from semiconductor technology. And so over the past month, we've assembled our approach and have done some initial calculations that we're eager for your feedback on before we further develop this proof of concept project. Briefly, my goal in this presentation is to describe what we've done, show you some examples of the calculations that we've proposed to do, and say a bit about our data thus far. I won't do too much on this last point, but as I'm going through this, I'm eager for your feedback on several points. I've listed some questions here that I'll walk through. Again, we'll come back to this at the end, but I wanted to pose these questions now so you all could think about what kinds of feedback you might have. So for example, when we talk about the kinds of activities that we think semiconductors may be enabling greenhouse gas savings through, what kinds of activities are we missing? What's your high-level opinion on our approach? What kind of scope are you interested in? I mean this geographically mostly, but there are other kinds of boundary questions that may come up. We've put together a model, and is that of use as you all continue to refine your own assumptions and understanding, or are you mostly interested in the results? We'll come back to this, but this idea of also figuring and accounting for the impact of manufacturing semiconductors, which you all have done a tremendous amount of effort in, could also be part of the assessment. In other words, do we want to look at some sort of net good result as opposed to just the enablement effects? This next question is particularly important to try and understand how does this effort overlap your existing or past efforts to make sure that we're adding value and not being duplicative with work you have already. And is there anything else we're missing in this consideration? So obviously, we'll come back to these questions at the end, but I wanted to start with them so you could think about them as we go through. So the first thing that we attempted to do was understand a bit about where energy is used within the global economy and therefore where opportunities might be greatest. Our approach in this project is really a bottom-up modeling where we think of application by application where semiconductors might offer savings, but we wanted to start by looking at the overall pie of energy use to try and decide how to break down which bottom-up opportunities we'll look at. I believe that you all have similar sorts of efforts that are looking at things more from a top-down perspective, so here's where I'd particularly like your input on whether or not these methods reconcile. So here is a Sankey diagram. This is data from 2010, so it's a bit old, but we have done some spot checking of this more recently and find these trends to be similar. So here we're looking at greenhouse gas emissions, various stages of their creation and consumption throughout the economy. Particularly, I'll draw your attention to this sector column here, as that's where we have focused on between sector and equipment basically. So the main contributions that we look at here are by transportation, buildings impact, industry, and agriculture. We have not looked further into agriculture, as that didn't seem like a dominant role for semiconductors, but please let me know if you think there's something that we're missing there. So here's world building energy use, again in 2010, just as a benchmark. So we can see that, first of all, the donut on the left here is residential energy use, and the donut on the right is commercial energy use. And we're looking at the total in terms of petawatt hours at the bottom here. And our left donut we can see is much more significant in the residential energy use than the commercial energy use. And you'll note that energy doesn't directly map to CO2 emissions, and we could consider the source of the energy, so the grid emissions, is an independent point of conversation if you'd like, but we've focused on this energy use as a way to direct our efforts. So here we see that in terms of the pieces of the pie that are most significant in residential, we're looking at cooking, space heating, water heating, and lighting. So these areas here are where we've focused our attention. On the commercial side, we're again focused on space heating and other here where IT equipment features as well. So If we do a similar sort of activity around transportation, we'll see that transportation, this is the graph we're looking at here. Now we've moved back to looking at greenhouse gas emissions. But again, over time, stopping in 2010 is where this data ends, and we see that 72% of those emissions are associated with road transportation. So the kinds of activities that we've looked at on transportation are focused on road travel, so largely automobile travel. And then we have not dug into industry in detail yet, but look to do that in the next phases of the work, and would also be very interested in your insight into where you feel like our efforts are best directed when we're looking at emissions associated with industry. And so what this set of tables is showing is which industry sector are we interested in, what the gas is, and what the emissions are. And so in particular, we think about the indirect emissions associated with the electricity and heat with industry as being one of the dominant sources of emissions. There's also this other category that has significant emissions as well. So now that we understand a bit about where energy is used, that helps to focus our second step, which is to describe the set of activities where semiconductors have an impact. So what I mean by this is where are semiconductors used where they may offer some enablement opportunities, and then we will propose a way to determine their enablement potential. So there's two parts of this that are useful to get feedback on. One is, are the set of activities that we proposed the relevant ones? Are there others that come to mind? And then the other piece is the way that we're proposing looking at their enablement potential make any sense? This second part is obviously fairly complex and has a lot of uncertainty associated with it. So we'll get into a little bit of detail around that. But even getting your input on the actual activities we're looking at is quite helpful. So this is a summary of the proposed focal projects that we've looked at, and I'll go into each of them in a bit more detail where we might have savings opportunity. So if we remember from buildings, we had broken that down both into residential and commercial buildings. Within residential buildings, we're interested in looking at smart home applications. And within commercial buildings, we're interested in energy management systems. We spent a little bit of time talking about transportation and really the role of automotive transportation and emissions. And so the set of activities that we've listed there are the use of electric cars, automatic start-stop systems, sensible driving, and speed limit observations. I think there are likely others within that, so I look forward to getting your input on that. And then finally, we've looked some into telecommuting, which relates both to transportation and building use. Others that we want to explore that we don't have detailed modeling around yet is energy management within the industry sector that we talked a little bit about, and be interested in your feedback around that, as well as telepresence. So that would be, again, going to the transportation side, avoiding particular travel, potentially not road travel so much as airline travel. So that's why we've put that a bit on the back burner. Another place to consider transportation would be in public transportation enhancements, so the kinds of monitoring capabilities that might increase the amount of public transit use by individuals, particularly in urban areas. So now we're going to review our models for each of these activities for your input. I'm not going to go in tremendous amount of detail on each of them because I'm much more eager to take time and question and answer, focusing on where you all have greatest interest, but I'm happy to answer any questions afterwards. So going item by item, we'll talk first a little bit about smart homes. So when we think about smart home or home automation, this is building automation that can monitor and control the set of activities that we do in our home. So lighting, heating, home appliances, and this is realized by using switches and sensors that are connected to a central hub that you can control things from a mobile phone. So this is convenience for managing the energy use at home, therefore potentially decreasing energy use. We've focused on HVAC, so heating, ventilation, and cooling, and lighting as the largest categories within this. Cooking also, as you may remember, was on the pie chart. We haven't focused on that as that doesn't seem to be as manipulable by the set of applications that I just mentioned. As you can see from the equation here, we're looking at the potential for energy savings as a function of what the energy use is in the residential sector, what percentage comes from lighting and what the potential improvement within lighting is, and then what the percentage within HVAC and the potential improvement with HVAC is. And then there's some emissions factor. Again, I mentioned that at the beginning that we can talk about as well at the end. So a couple of points I'll make on this approach. One, you'll see Based on this cartoon image here, there are several other kinds of things we could consider. So the use of particular appliances that may be more energy savings. And then I mentioned some of the cooking applications that we didn't look into as much. The other important piece of smart home is that we think that much more detail can be possible if we break things down by the type of residence, where it's located, climate, etc., etc. And so those are the kinds of details that we want to be adding and we're interested in your input around. A little bit more detail around the smart home, just because that's one where we've done some initial calculations. I haven't cited the data sources within these slides, but they're in the written report that was provided as well, so we can look to that if folks have questions. So there are two models shown here. The first one looks at savings as a function of what the CO2 emissions are within the residence and what a percentage expected savings is. So this is obviously very high level, very simplistic. One more level of detail is provided in this analysis where we talk about what the total residential energy use is in terms of BTUs, and then what percentage of that is due to lighting versus HVAC, and then what the improvements could be in each of those. And that comes together into a full greenhouse gas savings calculation. I won't go through too many more specific numbers in this presentation, but I thought it was interesting that these two methods come to somewhat similar numbers, even though the data are derived from very different sources. And again, as I said, the next step within this model would be to go into greater detail where we break residences down by type, by climate, and look in more detail at where those improvements are. The next aspect is energy management systems within commercial buildings. This is used for operators of electric utility grids to monitor and optimize the performance of the generation and transmission system within buildings. It's commonly used by individual commercial entities. Siemens has done a lot of work in this area, and so there's some data available through the company. Here, the equation that we're using is the energy savings potential essentially associated with a ratio, where the ratio has to do with when you're manually operating the energy management of a building versus some kind of automated system. I think there is significant detail we could add to this model in terms of type of commercial building, even breaking down similarly to the way that we did on the previous one in terms of lighting, in terms of HVAC, but this is a starting point that we'd be grateful for your input around. So a little bit more detail here. Obviously the total energy consumption we can break down by what that energy is being used towards. So is it electricity, is it natural gas, is it fuel oil? And then within each of those, Siemens had some data about where the savings potential is. Obviously, this is also very uncertain based on how effectively the energy management system is being used, and the kinds of benefits are going to vary as a function, again, of climate and type of building. So that's where more detail can be added, and we'd be curious for your input as well. So those are the two applications specific to buildings. Now we're going to talk in some detail about the automotive applications. I've skipped over electric cars, you may notice. This is because there's significant uncertainty associated with electric cars that we've proposed in this phase to not consider it in as much detail. But we've listed it on there and done some research on it that's included within the report. So now we look to the automatic start and stop system. So another way to save GHG emissions in vehicles can be realized by having an automatic shutoff. And this basically derives from the issue that when our cars are idling at stop lights in traffic, there's a lot of fuel that's expended. And there's variations on how much those emissions are expected to be, but they are significant. One study we found said that idling the car for just 2 minutes uses about the same amount of gas as going 1 mile. So there is a potential here to consider the application of an automatic start-stop system, which shuts the car down and then restarts it upon the light turning green, etc. So here the model we've thought through is the number of cars, what's the time to idle, and then there's basically this delta between the fuel that's consumed in idling and then the fuel that's then needed to restart the car. So obviously if the fuel to restart is greater than the fuel to idle, then this isn't going to be a good opportunity. The next activity includes two aspects: driving sensibly and observing the speed limit. And again, this is the kind of thing that can be facilitated by controls within an automobile. So the motivation for these stems from the fact that if we drive aggressively, speeding up, rapidly accelerating, braking, etc., this uses gas inefficiently. There's some data that we found that says that it can lower your gas mileage by 15 to 30% at highway speeds and 10 to 40% in stop and go traffic. This is obviously very dependent on the type of behavior of the driver and highly uncertain, but this is the kind of thing we can develop in more detail based on your feedback. The second idea is that vehicles are going to drive optimally at different speeds, but that gas mileage usually decreases rapidly at speeds above 50 miles an hour. So where that's a posted speed limit, observing the speed limit can also offer the opportunity to use gas more effectively. So this is a pretty straightforward calculation again if we look at it at a first order, where we're interested in the number of cars, what the distance they're traveling in, and then how are we deriving benefit from making our driving more consistent and traveling at the speed limit. And here we're looking at the emissions associated with petroleum versus diesel, depending on where it is we're looking at this. So there's a lot of behavioral studies that would need to be incorporated into this to give us a sense of the uncertainty associated with the savings, but that's the basic idea. So now we shift again to an activity that's been looked at in some detail in the literature, and this is telecommuting. So here we're saying that the method reduces road GHG emissions by switching the way people work. So if we're working at home, that we're saving our commuting travel. But we need to account for the fact that we're also going to have energy use within an office building versus our personal homes, and that you might also be adding some personal trips if you're working from home. So this model has a few different levels to it. At a high level, we need to think about how many people are telecommuting, and then what's the commuting emissions, and then the emissions associated with your home and your office, and then what your personal trips might be during the day. And each of those are calculated independently. So the greenhouse gas associated with commuting is really a function of the distance you're commuting and the fuel that you're consuming in that distance, and then how much you're actually saving in terms of how many days you're having work from home. And then the office versus home are similar to what we've looked at in the past, basically the energy used in the office as a function of the electricity emissions associated with that, compared to what's being used at home. And then we have this personal trips factor in here as well, because you may not be driving into work, but you may run errands during the day, etc. This one is hard to account for, but there has been more data that seems to indicate that if people are working at home, they're spending overall less time driving, which means that we're going to have net emissions saved from fewer cars on the road. This is just a little bit more detail on the kinds of data that we found around telecommuting. So this important information here is what's the weighted distance of the people are commuting that we'll be offsetting. So here's a table that shows in terms of the length of travel, what percentage of people drive that length. We juxtapose that with the number of days that people are commuting, and so this is what the potential for telepresence is to be used within a particular economy. So often these studies are done by particular regions, so we need to think some about how we scale them, depending on the scope that's of greatest interest to you all, and how granular we want that to be. So those were the set of models that we've developed. What I'd like to do now is get your feedback on the kinds of questions that I outlined in the beginning. At a high level, do you agree with our approach? What are we missing? What kind of scope are you particularly interested in, and how granular would you like that to be? A separate question, which we may not have time to get to, is this idea of including impact so that we're calculating a net good rather than just the benefit. I'd also like to hear about how this overlaps with your other existing efforts. In terms of what we're up to right now, we are continuing this quantification. I've given you some of the ways that we're doing that, but we'd also like to incorporate your feedback at this stage. One of the most important things for us is, given the fact that these are estimates, we need to carefully add uncertainty to this model. And so that's what we're doing. And that basically means we're going to be calculating this in the context of the ranges of data that we're able to find to determine which factors are most uncertain, therefore where should we get better data, or what kind of confidence can we have in the assessments. Obviously here I haven't aggregated our findings to give us one number of enablement or a range associated with enablement stemming from semiconductors, but that's obviously an important part of this project. I look forward to your questions and look forward to discussing more.